Okay, so today I'll move a bit from the building side to transportation, and especially on electric vehicles and individual transportation. And I'll drive you through a research project that we have been doing with a car designer to understand what's the impact of glass specification and particularly of solar properties on the the extension of driving range of individual electric vehicles. So first, a little bit of background where I'm coming from. So we are a building physics group in the Polytechnic of Torino. We are used to work on buildings mainly and different parts of the building. So looking at generally building energy performance of the building envelope, HVAC and renewable energy sources system, but also lighting and acoustics. And I'm part of the group that works with the performance of building envelopes. And within this group, we did a more like a small startup on special environments. And like special environments for us, coming from like a building and facade perspective, are environments like vehicles, boats, marine industry, so generally transportation. But we are also working with spacecraft, so space industry, as well as museum and showcases, and the reason we are working with them because we are aiming at improving the performance of these spaces from the perspective of energy efficiency, of potentially comfort of the condition that we want to keep in these spaces. So it's not much different from the building environment. Which is as well performance-driven. What is changes is actually the technologies that you can use and potentially the specification and the boundary conditions. So generally related to buildings, I'm personally working on, my work is focused on smart glazing, so on characterization of novel smart glazing technologies. So we've been working in our group for some years in including phase change materials in glazing. We've been working with thermochromic and thermotropic glazing with different kind of electrochromics, and we are now looking at new nano-enabled electrochromic glazing, including also not electrochromic technologies like micro blinds or micro mirrors. And as well, we are looking into how to best integrate these technologies into the building. So looking at things like how to optimally control smart glazing from an energy perspective, so increasing the energy efficiency by means of model-based control, like model predictive control, but also from the occupant perspective. So trying to put the occupant at the center of the control and understanding how to improve visual and thermal comfort, but also quantifying and minimizing thermal actions in high performance and smart glazing, and understanding how this can be integrated into marine and automotive sectors. So coming to today's presentation, I'll drive you to a bit of the motivation of this study and then the specific vehicles and the envelope that we are designing, which is this pop-up project. And I'll drive you to the methodology that we've used, which is not really a standard in let's say current automotive industry related to internal combustion engines, but is pretty much becoming a standard for electric vehicles. And then we'll talk about the impact of glass properties on the mainly air conditioning loads. And finally, what's the impact of this air conditioning load in the driving range of an electric vehicle? So first of all, a little bit of background on the electric vehicle market. We have seen, like in the last keynote of Wednesday, as the share of electric vehicles is quite ramping, and as well the increase in in the market and how many electric vehicles are sold annually is quite increasing. So there's a plus 56% more between 2016 2017. But there are still a lot of issues to overcome to make like an electric vehicle as a like mass. Like autonomous electric vehicle as a mass product. And these issues are mainly related to the low driving range per single charge of the electric vehicle for their batteries, which is mainly due to the very low energy intensity of the batteries that are currently used. Like just to compare, for example, to a fuel tank, in order to drive the same distance, an electric battery would weigh 30 times more than what would be needed for internal combustion engine. And then there are long recharging time, limited number of recharging stations, but let's see what we can do in order to increase the driving range per single charge. And so one thing is increase the energy density of the batteries, but the other thing is reducing how much energy is drawn by auxiliary system in the car. And like if we look at what are the auxiliary systems that are using energy of a battery, and we compare, for example, internal combustion engine with electric vehicles, we can see as the main source of the main usage of energy after the traction, the motor itself, is actually the air conditioning. So keeping a certain temperature and comfort level in a car. This was not such of a problem in internal combustion engine because, of course, you have waste heat during winter at a certain temperature that can be used for heating the car, but also it's not so energy intensive for the cooling compared to what is used for the traction. While in electric vehicles, this can represent up to let's say between 10 and 50% actually, depending on the boundary condition and the driving style and many parameters of the driving range itself. So the question is, how can we actually minimize the air conditioning energy and loads in electric vehicles? So there are different, like three main strategies that we can use. One is actually to optimize the cabin and to optimize the envelope of the cabin itself by means of, let's say, passive strategies. So optimizing solar properties of the glazing that we are using, or the U-valued insulation properties of the opaque part, as well as adopting some active technologies like smart glazing into the glazing part, or improving the efficiency of the HVAC that we are using, or as well improving how we control the HVAC with some smarter control methods. So today we'll just focus on a study concentrating on how to improve envelope characteristic and the design of the vehicle envelope. So the case study which I'll present you today is this pop-up project. So is basically a project that is a concept car that is designed by Giugiaro, Italdesign Giugiaro, which is a car designer, and the let's say the project was done together with a team of students of this Alta Scuola Politecnica, which is an excellent school between Politecnico di Torino and Politecnico di Milano, that are working with multidisciplinary team on a specific project. And the project itself, the aim of the project is to understand how to increase the driving range of this specific vehicle. Now, coming to the concept that is behind this vehicle, so it was thought by basically Italdesign Giugiaro and Airbus as a multimodal electric vehicle that can be used for autonomous drive and car sharing into mega cities. And basically it couples a roads module with a flying module. So you can either choose which one you want to drive. And we were focused more on the battery capacity of the road module. This could be used in car sharing scenario. So you can basically see the car from your mobile, you register to the app, and then you book the car, and then you just use it. But if, let's say, if you're changing and you're increasing your driving range, it means that you can use the car and leave it not in a recharging station so often, but you can use it in bigger distances, and you can also leave it in, let's say, not in a recharging station most of the time. So actually, it was very important in their business model to increase the driving range so that the car sharing part between one charge and the other could be extended. So we've been looking at, let's say, what is the process of understanding how to size the HVAC in the automotive industry. And when we look at internal combustion engine, most of the time this is not based on a model, on a prediction model, and based on real calculation, but most of the time is based on data and experimental data of past series of car. And this is done after the prototype is actually designed. So there is not much feedback between the concept design and the sizing of the HVAC. While in the electric vehicle industry is more and more important to actually understand what's the impact of your concept on the HVAC size and the HVAC usage of energy, and on the driving range and the capacity of the battery. So we basically applied this methodology to this case study, and we use this Amazim software, which is a proprietary software that is used in electric vehicle industry, in order to have precise HVAC sizing and also being able to customize the envelope. So what we did, we defined our base case, which is our standard, our baseline design. So it's a small car for two people, so there are 2 seats, 3 cubic meter volume, 13 square meter envelope, of which 25% more or less is the glazed part. So if you do a rough estimation of the surface on the volume ratio, is something that is pretty close to other electric cars that are commercially available at the moment. So about between 0.2 and 0.25 volume on surface ratio. And the characteristic of the building envelope of the baseline was for the windshield, normal laminated glazing, 3+3 with an interlayer, while monolayer glazing for all the others that were not windshields. So the transmittance, the total solar transmittance of the glazing is about 0.8, and this is not to limit the visible transmission that has to be above 70%. And in terms of U values, it's pretty high, so it's about 6. While the opaque part, which represents the other 75%, has a U value of about 2, which is mainly represented by the air between the opaque laminates. And so most of the surface is the opaque part. And so we've modeled, we did a thermal model in the Sim Center Amazon software of the car, and we tested this model in 2 different conditions. One typical summer condition, which is called pull-down test in the normal car industry, which basically simulates a car that is left in unshaded area for 1 hour, so with 1,000 watt per square meter of solar radiation on the car, 40 degrees C outside, and then after 1 hour, like you switch on the air conditioning and you try to bring as fast as possible the temperature on your forefront more or less at 28 degrees C. And so this was the dynamic part. And then we waited until we get 22 degrees into the car, which is the comfortable level. And then we repeated the same test for winter condition, which is basically no radiation and minus 20 degrees C outdoor temperature. And then finally what we did is that we ran a sensitivity analysis by changing the properties of the glass itself. So we changed basically the absorption, the transmission, the reflection of the glass in a range that goes between 0.1 and 0.8. Of course, the sum of the three has to be equal to 1. And then we changed also the transmission, the U value of the glazing in like a sensible range between 5.9, which is the baseline, and 1.1, which is a, let's say, double glazing unit with 6 mil argon and low E coating, even though it's not realistic for a car, but we wanted to understand what's the sensitivity, what's the impact of having an IGU on a car, for example. So the performance metrics that we use are, let's say, the air conditioning load in steady state conditions, so at the end of the test when the 22 degrees was reached, and then the air conditioning size, which is basically the peak load that is needed after 1 hour in unshaded condition of the car to bring the temperature down to 28 degrees. Then we check the air and seat temperatures, which are actually kind of measuring the thermal comfort of the occupants, and it is really important as a performance metric in how much time do you go from the peak temperature to the 28 degrees on your forehead. And finally, our performance metric are what is the total consumption of the air conditioning in a driving cycle in an urban environment, so 30 kilometers per hour, more or less, and how much this improved air conditioning efficiency and improved envelope affects the driving range of the electric vehicle. So just looking at the base case, so like baseline design, so the glazing is almost a U value of 6 and the total solar transmission of 0.8. So we can see the difference between the loads in the summer case and in the winter case, and we immediately see that most of the load is represented by radiation. So 67% of the load is represented by radiation through the glazing and through the opaque part, and 57% is just the one through the glazing, while a very small part is actually due to the temperature difference between outside and inside, both in summer and winter. So we decided to concentrate on the summer dynamic condition. And then when looking at instead the this graph, bottom left, is the temperature inside the car. You can see that left in unshaded condition for 1 hour, so 3,600 seconds, the air temperature goes to about 80 degrees. And then for the air conditioning, it takes about, in order to reach the 28 degrees, it takes about 8 minutes, so 500 seconds, more or less. Then next step is to run a sensitivity analysis. So we change the glass properties and we see how that impacted the total load. So basically we changed the solar transmission of the glazing and the absorption and the reflection. Of course, the reflection is not represented here because it's the complementary to one of the sum of absorption and transmission. And here you can see the total loads, and basically you can actually reduce the total load of the air conditioning by 57% just by improving the glazing properties. On the other side, instead, you can see how much the U value, so improving the thermal properties of the glazing, which is this 25% of the total envelope of the cabin, how that can impact the total the total load, and this actually only comes to 2%. So it doesn't make much sense for this case to improve the thermal transmittance of the glazing itself. Then looking at the temperature inside the cabin, the main difference is not regarding the peak temperature, at least for what the air temperature is concerned. So the left graph, your left graph. It's not about the peak because you can reduce the peak by 10 degrees with transmission of 0.1 and absorption instead of 0.8. But what you can do, you can reduce the time that it takes you to reach comfort condition. So instead of comfort condition being reached in 8 minutes, that maybe is the time that you drive your car until you leave it in the next station. Like thermal comfort can be achieved in just 2 minutes and 30 seconds, like 200 seconds, something like that. But also very important is the radiant temperature, so the temperature of the seats. In this case, were quite black seats, so like 0.95 absorption. And you can see that actually the difference in the seat temperature, also at peak condition, can go up to 60, 70 degrees. So it's a pretty big difference in terms of potential thermal comfort. So this is from the analysis side. Now, then we try to assess which kind of technologies we could use, not increasing the weight of the glazing itself, and so not having a cavity at all. And so basically, we couldn't use any silver-based high-performance coating at all. So the technologies are very restricted. But still, so potentially go back. So base case is the clear, laminated clear glass for the windshield and just a monolithic clear glass for the rest of the car. And so we could use some tinted glass or tinted PET interlayers or XIR interlayers, so interlayers that just reflect or absorb the infrared light selectively, or some high durable coating, so our metal-based coating that can be used on the interlayer, so you don't need a cavity. Or technologies like electrochromic or suspended particle device or potentially liquid crystal. The problem with liquid crystal is that you would need current power also to maintain a certain bleach state, so continuously. So potentially when you leave the car, the let's say the glazing will go black, so will go tinted if the state is not, if you don't have any power. So we also had a look at different other glazing, like smart glazing technologies, but there are lots of constraints in terms of curbability, having visible light transmittance which is higher than 70%, maintain a specular state when switching, needing the need of a cavity, or potentially the scale and the speed of the switching mechanism. So we're just concentrating on finally on electrochromic and SPD technologies to be embedded in the car. Finally, what you can see here is actually a match between what we could use in terms of glazing technologies and what could be the impact. So on these two graphs, what you can see here on your left, each point represents a certain glazing, a static glazing technology, while in terms of G value, so the total solar load that is emitting through the glazing, and in terms of visible transmission. Now, for the windshield, we can just use glazing that are above, let's say, 70% visible transmission, while smart glazing are instead represented by this dashed line here. So they can switch in a state between their maximum here and the minimum state. And also these K lines, these ISO lines that you see here represent selectiveness of the glazing. So how much visible transmission they have. So the ratio between the visible transmission and the G value. And so the lines there for example, the selectiveness of 1.7, 2.2 are actually representing silver base, double and triple silver base coating, just as a benchmark, a comparison. And then on your right side, what you can see is the impact of these glazing technologies on the load of the car. So you can see immediately how they're very promising because are quite selective compared to tinted glass and tinted interlayer are XIR interlayers. While also very interesting option would be to switch the states of the glass, so your optical properties between a bleach state and a tinted state. For example, in a car sharing scenario where you are actually booking the car already knows that you are getting there. So already the automation of the car can regulate what's the best for the glazing and the air conditioning, and then you can potentially decide to switch on and off your windshields when you're driving or when you are when you're stopping. So finally, we did an estimation of using the best technologies, in this case the electrochromic, on the HVAC size and their efficiency. And in a summer scenario, we could reduce the loads of the air conditioning between 2.6 and 1.7, and the peak load, so the size and potentially weight and cost of the HVAC of 25%, so between 5 and 4 kilowatts. Then, looking at how much does this impact on the driving range? So we just calculated with a simple comparison, considering a coefficient of performance of the HVAC of about 3, how many more kilometers for a single charge you could do. But of course, this depends on the total capacity of the battery and how efficient is your electric motor. So we did it for the pop-up, so this case study here, the pop-up, but also we try to contextualize to nowadays commercial vehicles, but also potentially future vehicles where you have an efficiency of the electrical motor which is actually double and the same capacity. And we've seen that the impact of the glass changes between 5 and 10%, more or less. So concluding, low driving range is quite an obstacle to market penetration, and the air conditioning energy use can draw energy from this battery between 5 and 50%, but actually we can optimize the envelope in order to get between 25 and 35% less air conditioning load just by optimizing the glazing, and this could impact on the driving range between 5 and 10%. Although what we are doing, we're not just looking at the glazing, but we are doing also in other ways to improve the envelope and the efficiency. And we've seen that actually, just by some preliminary calculation, this can change the driving range between 15 and 25%, which is quite a big number if you consider that an electric car can be maybe driven for 400 kilometers, and maybe 100 of these kilometers can be actually increased by just optimizing the design of the envelope of your car. And just final thanks to the students that actually were part of this project. And basically, this is actually one of the first prototype of the car, and we cannot show the others because there were also other partners involved lately that were not part of the original project. Thank you very much. Hope you enjoyed.
And now we can take questions, even though we went a bit over time, but no matter. There's a question.
Thank you for the presentation. On this demo car, so actually did you realize electrochromic glazing?
No. So next step at the moment, the project is still going on. And yeah, I mean, it's... we should look at film technologies and electrochromic technologies that can be actually curved. So next step would actually be talking with companies and to see whether we can integrate their technologies or some development needs to be done. But we are talking about 10 years 10-year time. So the first demo will probably be in 2028, 2013. So there's quite a long time ahead for development. But yeah, that's the intention, using electrochromic glazing. Yeah.
Further questions? That's in the corner, back corner.
Your presentation mostly considering summer conditions.
Yeah.
So what about in winter conditions? Would double glazing be an advantage in that case? Because in your presentation it didn't give any advantage, so only 2%.
Yeah, so there was just summer condition. In the winter condition, yes, it could give an advantage, but it could also give a disadvantage in terms of additional weight that you're giving to the car, and like you're using more energy for the traction and not maybe for the air conditioning. Although in the winter, the normal test that you do in like the pull down test for summer, it doesn't consider solar radiation. So actually, lots, like when you have sun, lot of your of the heat that is lost through the envelope is actually balanced by radiation. So even if you can have a large impact on, let's say, your design scenario, actually this will be reduced a lot when you consider the actual condition when you drive. But it's definitely something that we are that we will do to understand what's the impact on the, let's say, on a yearly use of the car in this car sharing scenario. Yeah.
Hi there. Did you like what you just saw? If you did, why not like the video? Drop us a comment below, as well as share the video with others, since GPD is all about sharing. And to receive more videos in future, subscribe and don't forget to click the bell icon for notifications. Ciao.